So all the reactions at A, I need to determine first in the free body diagram what those reactions are, and then I need to solve them numerically. And I want to know the tension in cable BC. I am given that the weight is 300 pounds. And the diagram, and that will all be reflected in my free body diagram. So that's the extra information that is not in the diagram they gave us. The free body diagram step, again, this should be kind of the toughest step once you get the equation writing down and the solutions down. We need to first pick what is our object of interest that we're going to isolate from all of its connections. And then we have to draw on there what those supports, what those connections did to our object. So to pick our object, we want to look at what are we asked to find, because if our object isn't going to have this affecting it, then we're not going to be able to find these unknowns. So looking at the diagram, what object, when we isolate it from what it's connected to, will give us the reactions at A and the tension in BC? Right, so if we isolate that blue rod, we're going to disconnect it from those brackets at A. We're going to cut the weight away. We're going to cut the rope away. Everything we remove, we then have to model what the things we removed did to the object we kept. So if we just keep that blue bar from A to B, kind of that T section, and use that as our object, we're going to see the reactions at A come through, and we're going to see the tension in BC. So I'm going to keep the coordinate system that they gave, where A is at the origin. The bar comes down here. It goes up into the right. There's another piece here that actually turns out it's not going to matter, but I'll keep it. We'll have point B. We'll have a point, I'll just, for convenience, call this point D. And we have point A at the origin. Again, this is the object that I'm keeping. I'm not keeping the rope. I'm not keeping the weight that's attached to it. I'm not keeping at least the brackets at A. So I'm not keeping the pin connection at A. So on my object, I'm first going to draw what the applied forces are. In that case, we have the weight hanging down at, in this picture, I called it D. And we know that the force of that weight is 300 pounds. It acts in the negative Z direction. All right, that's the only applied force on it. What other forces or couples are going to act on the object that we kept? Right, at point B, since I did not include the rope, I'm including what the rope does to my object. Well, it can only pull, and it pulls at B, and it heads towards point C. And I don't know its value, but it's something that I'm looking for, TBC. I removed it from A, where there was a pin connection, so now I have to, that's a support that I have to model. What did the pin do to my object, which is to say what motion was prevented because it is attached to the pin. And I consider that in isolation. So first let's consider the translation that's prevented because it's connected at A. All right, so generally we can think of it in the X, the Y, the Z directions because usually it's oriented that way. But really we can think of, does the pin allow translation, or what translation does the pin prevent from happening? Along the x-axis, can we move it left or right because it's connected to that pin at A? Right, we can't move it, so I can include a force because that motion is prevented. I'll assume it's along the positive x-axis. In the y direction, can we move it along the y direction because it's pinned? Right. That's prevented, so there's a force. And Z is the same story. We can't move it up or down the wall because it's pinned at A. So there will be a force AZ. So in this case, we have all three components of force being exerted here. Now we consider rotation. Again, we can consider one axis at a time here. Around the x-axis, is it prevented from rotating or allowed to rotate? It's allowed to rotate around the x-axis. When we're thinking about what is prevented or allowed, we don't think about the rope. When we're thinking about here, we only think about does the pin allow it or prevent it. We don't think can the object actually do it or not. It's in static equilibrium, so it shouldn't be rotating. Yeah, it's not rotating, but the pin is not the thing preventing rotation around x. It can rotate around x, so I don't draw a couple. Can't rotate around the y-axis. Right? It can't because of the pin there is going to, if we tried to twist it around y, it would bash into the bracket there. We cannot rotate around y, so there is a couple. I can draw that. I'm going to assume in the positive, around the positive y-axis, and I'm going to call that my. Cannot rotate around y, so there is a couple. Around z, we have the same issue. Can we twist it around that z-axis? Right? If we try to do that, again, that pin is going to hit the bracket and prevent that from rotating. So it cannot freely rotate around the z-axis at A. So there's also going to be a moment, I'll assume, around the positive z-axis. I'll call that mz. At A, we have three forces. We have two moments. We have another force TBC over here. If we look at our free body diagram, we have a total of 6 unknowns. So I'm going to write the coordinates of these points. And that leads us then to the next step. C is at negative 102 feet. A is at the origin. Point B, where did it go here? Negative 460. And what I'm calling point D, where this weight is acting, negative 260. Now I have the dimensions. Now my free body diagram is complete. And I would have known it's incomplete right away because the first thing, or what I suggest the first thing you do for the equation step, before we write our equilibrium equations, what should we find first? Right, the unit vectors, and to find unit vectors, these coordinates we are going to need. AY, AX, AZ only act along X, Y, and Z, so those are fine. The weight only acts along Z, so that we don't have to worry about. What we want to find is the unit vector from B to C, so that we know how much of the tension is along X, Y, and along Z. And that'll make the equilibrium equations easier to write. I won't go through all the steps, but we do C minus B divided by its magnitude, and we get that U hat BC is going to be 3/7 I minus 6/7 J plus 2/7 K. Now I'll start writing my equilibrium equations. Like in 2D, the order doesn't really matter that we write them in. I tend to in 3D because there's a lot more to keep track of. I almost always do sum of forces X, Y, Z, and then the moments. In 2D, when you only have 3 equations, then it's oftentimes best to start with a moment. But here, just to be a little bit more methodical, make sure I'm keeping track of everything, I like to maintain the same order every time. From the free body diagram, looking at forces in the x direction, AX is in the x direction. AY and AZ are not. Those are couples. This is in the z direction. I have a portion of TBC, though, in the x direction. 3/7 of it will be in the x direction. One equation, but 2 unknowns. I'll set aside for now and come back to it once I have some more information. In the y, I have all of AY. This is in Z, and I have some portion of BC, negative 6/7 TBC. I now have 3 unknowns and 2 equations. So again, I'll just leave them up here for now. I won't try to solve anything yet. I'll go on to the Z direction. AZ minus 300 from that weight plus 2/7 TBC. I have now 4 unknowns, but only 3 equations. Sometimes, and you'll see in the other example in the video from today, sometimes you'll have 3 equations, 3 unknowns here, and it becomes solvable. Sometimes you don't. In this case, we have more unknowns than we have equations so far. So I'm just going to put them aside and come back to them later. They're still useful, but I can't get numbers yet. All my force equations are done, so I can generate 3 more equations by taking the moment around a point. So I'll generate 3 more equations if I take the moment as a vector and set it equal to 0. Looking at the free body diagram, what does it appear will be the best place to take the moment about? Right, A is good. Number 1 is the origin, which makes it the position vector a little bit easier to find. More importantly, we have 3 forces that act at A, AX, AY, AZ. By taking the moment at A, none of those 3 will not appear in this equation. When I'm writing my vector moment equation here, I tend to start with any couples that are acting on my object. So in this case, what couples act on the object that we chose to keep? Yeah. Right, my and mz. What do I need with my and with mz in order to be able to use this in an equation, in the equation I'm writing? This is a 0 vector. This, as I've written it right now, are scalars. I can't have a vector equal to a scalar. So what do it's not just my, it's my times what? Right. And it's not mz just, it's mz times k. You must, for any couple, you have to include the direction about which they act. So the my is around the j-axis, the mz is around the k-axis. We need ijk terms on the right because we'll have ijk terms on the left. In subsequent steps, we're going to pick out just the coefficients, but when we're writing the vector equality, these need the correct directions associated with them. Now that is a j, that is a k. What else is going to contribute to the moment around point, I forgot here, in point A? Right, the 300 pounds. So we have forces that do not act through A will create a moment around A. And remember in 3D, we want to use a cross product. So we need R cross F. So in this case, the moment arm to the weight is going to go from A to D. And that will be crossed with minus 300K. We'll also have a moment contribution then from the tension that's acting at B. Because again, that does not pass through A, so it creates a moment around point A. So I also need a cross product, RAB, cross with the tension as in component form BC. I can rewrite this just like I did in chapter 4. I can expand this out. The cross product I can write as a determinant. This will be in feet, and this is in pounds. So my first one, RAD cross negative 300. RAD will be the coordinates of D minus A, which is at the origin. It will just be negative 260. And this is just negative 300 in the K. And the second cross product, I can expand out into a determinant. RAB will be coordinates of B minus coordinates of A. B is at negative 4, 6, 0. This last step is going to be a little bit tricky because in this particular problem, we don't have a number yet for TBC. I have to put the components of TBC, but it will have variables in it. The x component as we know now, or the I component of TBC as we know now, is going to be 3/7 TBC. The j component is negative 6/7 TBC. And the k component, 2/7 TBC. I would say if we knew by now what the number was for TBC, write it this way, but then immediately write the numbers here. It's going to make the calculations easier. We would rather not do this with the variables, but right now we don't have a choice. So when we expand these cross products, we will have a variable in them. Right, the MYJ I just copied, MZK I just copied. I can now take these determinants and expand them out. Remember what happens from chapter 4. When we expand out the determinant, we have IJK come out from this. We have IJK come out from this. And we have a J and a K here. I'll skip over a couple of steps. But what we want to do is we want to group all of the I terms together, all of the J terms together, and all of the K terms together. So when we do that, expanding out these two cross products, we will get negative 12/7 TBC minus 1800 times I hat. If we group the J terms together, we have MY. We get a minus 600 out of this cross product. And we get a plus 8/7 TBC out of the second cross product. And the K components will have MZ, since that has a K attached to it. We get 0 from this cross product. And from here, we're going to get 6/7 TBC. K hat. Yeah, I skipped over the actual expansion of these, but we get I's, J's, K's. I've collected all of my like terms together, and now I have a coefficient in front of I, in front of J, in front of K. And that's equal to the 0 vector. As I said earlier, this is actually 3 equations in one. What I can do now is individually, each of these coefficients has to be equal to 0. So my fourth equation is going to be from this coefficient, 12/7 TBC minus 1800 has to be equal to 0. From equation number 4, the only unknown I have is TBC. So I can use this to solve for the tension in BC. And I get that TBC is going to be 1,050 pounds. Now things start to kind of get pieced together. Now that I know as a number TBC, looking at equation 1, 2, and 3, I can find these 3 forces as well. I can put my value in for TBC, and I'll get AX using equation 1. AX is going to be negative 450 pounds. Fortunately, I don't have enough room up here. Sorry, it's all over the place. If I put in my value for TBC now into equation 2, I'll get my value for AY. AY will be a positive 900 pounds. And likewise, in equation 3, putting in my value for TBC, I can find AZ. AZ will turn out to be 0 pounds. It turns out that there is no force exerted along the Z direction on the pin. The free body diagram, though, doesn't know that. We're just drawing what it does prevent from happening. It doesn't mean that it needs to exert any force or any couple along that direction, but that's at the math step, we'll be able to determine that. We have all four forces found now. We still have those two remaining unknowns, the two couples that were at point A. But I still have those two more equations I haven't written yet. If I make my J coefficient from the moment equation equal to 0, I have my minus 600 plus 8/7 TBC. Because I know TBC, I can find my from equation number 5. My is negative 600, and this is foot times pounds, so pound feet. And I still have my K coefficients to set equal to 0. I have mz plus 6/7 TBC. Once again, I now know the value of TBC, so I can find my last unknown, mz. mz, I get negative 900 pound-feet.